All right, so we're going to look at Unit 4.6 here, dealing with local linearity and tangent line approximations. Basically, what we have here is if you have some sort of function, and say we want to look at the tangent line at a specific point there. Well, as you get closer and closer, as you keep zooming in, basically you get the exact same line. The line almost ends up overlapping itself. When you're looking at a tangent line, as you zoom in as far as you possibly can, that's called local linearity. The more local you get, the closer it becomes to looking just like a straight line. So imagine, thinking on your calculator when you graph a function, if you keep zooming in, eventually all your pixels are just going to go in one straight line, and it'll look like a line, even though when you zoom out, it could be a quadratic or a cubic or who knows what else. Now we're going to use that to be able to do some approximating here with our functions. So let's just get right into an example. And they're saying, okay, if f of 4 equals 5 and we have this derivative value, they want you to be able to use that to estimate a value. So basically, it's like we're saying we know what this function value is. We want to estimate what this here is at the next point. So in this case, the values were, this is like the ordered pair 4, 5. They want to know, well, they're actually going in the other direction, so I should estimate maybe right here for this point. And this ordered pair being 3.8, comma, we don't know. It's like we're trying to find out what this point is on our graph. So that's what we're going to find out here in this problem. Well, the way we can do that is basically we can use this tangent line, and we can, well, say, well, hey, it's not exact, but we know it's going to be pretty close based on a straight line versus a not straight line. We can estimate what the difference is, or say that there is going to be a slight difference, but we can be pretty darn close by following that pattern. So what we're going to do is, this is basically just a fancy way of doing a point slope problem. Y minus y1 equals m, x minus x1. What we want to find out is this value of y. That is what our f is going to be. Our f of, what do they want, 3.8. So basically, we have two different points. We have an x and a y. We have an x value of 4 for a y value of 5. We want to know the x value of 3.8, what the y value is. We don't know that. So that's what this y is. So y minus the other y value was 5 equals m. We'll come back to that in a minute. Our x values, well, we want 3.8 and 4. So notice it's just like finding your old school point slope, plugging in and making sure everything lines up. Now the issue is we don't know what this m is. Well, guess what? In calculus, m means derivative. So I'm just going to plug in 3 for that equation. Just that simple. And all you need to do is solve for y. So f of 3.8, which is equal to y, and that's going to be, when you solve this, you have 5 plus, what is that, 3 times negative 0.2. So you can use that in a calculator, or you could just leave it just like that as your answer. It ends up being an answer of 4.4 as your approximation. And that's important. This is an approximation, so make sure you have that this is approximate in your answer. All right, now, the next part of the problem asks is that if the function is concave up, is this estimate an overestimate or an underestimate? Well, here's how we're going to look at that. Ignore for now finding whether it's concave up or down. We'll learn that in future lessons. Basically, concave up looks like a cup. Concave down looks like a frown. If I am to do any sort of tangent line approximation here, on a concave up, if I try to do a tangent line right there, notice what happens. My approximation value is always beneath what the actual function value is. Even if I did that over here, my approximation value is always under my actual function value. So if f is concave up, that means that this approximation is an underestimate. And when it says explain, literally your explanation is because f is concave, in this case, concave up. It's just that simple. I draw the picture every time. You can memorize that concave up turns into an underestimate and concave down turns into an overestimate, which you can see here if I do that. Look, my tangent line is always now above the actual graph. Or I can just draw it out and fully explain it to myself, basically, because otherwise you may confuse yourself and get it mixed up. Okay, so that's all you have to do with concave up and concave down in determining over or underestimate. Here's another example. This time, instead of giving you function values, they're just giving you f of x in total. And it's telling you right away that the function is concave down at x equals 1. So the first thing they want to do is to have you find the tangent line at x equals 1. So we're going to go through the same steps. Y minus y1 equals mx minus x1. We should be able to find a tangent line approximation at x equals 1. Well, that means that I'm going to be plugging in 1 for x. The issue is I don't know what my y value is right now. Well, guess what? I can figure that out pretty easily. I just plug in 1 into that equation. So it'd be negative 2 times 1 cubed plus 5 times 1 minus 2. So negative 2 plus 5 minus 2 looks like that's negative, or not negative 1, positive 1 as my value here. So that becomes a minus 1. If they want just the straight up tangent line, we have no other x value to approximate it with. So that x and y has to stay the same this time. The only thing that's left is to find the slope. Well, the slope, it's the exact same way we just did it. Slope is equal to, let me change my color here. Slope is equal to the derivative. So the derivative is negative 6x squared plus 5. Well, we don't want any old slope. We want it at that specific x value. So I better plug in a value of 1, and it looks like I get a slope of negative 1 again. Lots of 1s floating around. So negative 1 is my slope. So there is a perfectly fine tangent line for you to use. And no, you don't need to get y by itself. Why would you? Don't do any extra work. Now, they want you to use that line to approximate f of 1.1. So here's what we're going to do is we're going to use that same equation, but now we're going to plug in 1.1. Well, okay, nice and easy. And now we just solve for y. So y is going to equal, we're going to have 1 when we bring that 1 over. Negative 1 times 0.1 is just negative 0.1. So that equals 0.9. So this right here is your approximation for f of 1.1. Now all that's left is to answer whether this 0.9 is an overestimate or an underestimate. So here is my answer for part B. To know whether that's an over or underestimate, again, I'm just going to draw it out. We said this was a concave down function, which means if I draw any sort of tangent line here, my estimation is always going to be up above the function. So that tells me that this is an overestimate. And why? Because f is concave down. Okay? Use abbreviations, help yourself out. But that's it. That's how you set up local linearity and linear approximations to be able to evaluate and analyze functions.